Every year, over 300 million electric motors are manufactured worldwide, from miniature ones that spin coolers in laptops to giants that power trains, factory lines, and mine elevators. And each one of them is not just a coil of wires and iron, but a complex system of dozens of precisely calibrated parts. How is the heart of a machine born? Why is winding similar to weaving and balancing to jewelry making? And how does one spark power a rotation that will last for thousands of hours? Let's take a look behind the scenes of one of the greatest technical processes, the creation of an electric motor. Inside every electric motor is a true mechanical electrical universe. The main components of a motor are the stator, rotor, shaft, bearings, housing, as well as a cooling system and terminal box. The stator is the stationary part, located in a circle inside the housing. It's what creates the magnetic field that makes the rotor spin. Inside the stator is a core made of layers of thin electrical steel, which reduces losses from eddy currents. In the slots of the core is a winding of copper wire, connected in a special way to create a rotating magnetic field. The rotor is the moving part inside the stator. It either has its own winding or is made in the form of a squirrel cage, aluminum bars cast into a steel core, which form closed current loops. When the stator's magnetic field interacts with the rotor, it starts to rotate. The shaft is a rod that passes through the rotor and extends outside the housing. It's on this shaft that pulleys, impellers, reducers, or other drives are mounted. It transmits rotation to the mechanisms. The shaft must be precisely centered. Otherwise, the motor will vibrate and wear out quickly. Bearings, usually two, one at each end of the shaft. They ensure smooth rotation with minimal friction. For reliability, they are lubricated with special greases or are sealed. The housing protects the internal elements from dust, moisture, and mechanical damage. It often has fins for heat dissipation or even a fan. The material is cast aluminum or cast iron, depending on the power and purpose of the motor. The cooling system, most often it's simple air cooling, a fan on the shaft drives air flows through the housing. In large industrial motors, liquid cooling or external air circulation through special channels is used. The terminal box is on the outside of the housing. This is where the power cables are connected to the stator winding. Inside, contacts, clamping screws, and sometimes temperature sensors. In the depths of the factory, in a workshop that smells of varnish, metallic dust, and warm insulation, stands a giant stator. A stationary ring with slots around its circumference. This is its core, made of thin steel sheets, tightly pressed together. In each slot of this ring will lie copper wire, carefully laid, loop by loop, turn by turn, because whether the motor will rotate at all depends on this. Before starting the winding, the stator frame is thoroughly prepared. The slots are lined with special insulating liners, like nests for the wire. These are materials that withstand high temperatures, vibrations, and electrical loads. And only when they are sure that the insulation is perfect, the winding machine is started. The machine, resembling a giant spool that unwinds copper wire from a bobbin, wraps it around guides and lays it in the slots. Everything is automated, but under the supervision of a specialist. One sharp movement, and the wire could lay with a kink or snag the insulation. And that's a potential short circuit. For powerful or non-standard motors, winding is done by hand. A worker inserts the wire in a loop, pulls it through with a tool, presses it to the bottom of the slot, secures it, and tightens it. The work is similar to weaving, but with shiny copper and immense responsibility. Each coil, and there are dozens of them, must be identical, symmetrical, and correctly oriented. After the first layer of winding is completed, interphase insulation is laid, and then the second layer is placed. The wire forms closed loops, phases, which are then connected in a star or delta configuration, depending on the motor's setup. Then, the wires are secured with strings or plastic fasteners, The tension and geometry are checked, and if necessary, adjusted by hand. And finally, impregnation with varnish or epoxy resin, so that all this doesn't shift even a micron under vibration and temperature under load. If the stator is the skeleton, then the rotor is the muscle. It moves, rotates, creates torque. It's not visible when the motor is running, but it's what drives everything, from a fan to a train. At the core of the rotor is a steel shaft, long and powerful. Around it, the core is mounted, a set of thin electrical steel sheets stacked into a cylinder. The sheets have slots. These are for the conductors. This is where the most interesting part begins, creating the winding that will make the rotor come alive. One of the most common options is the squirrel cage. Aluminum or copper bars are inserted into the slots, and both ends are cast into rings, like a hoop around a cage. This creates a closed current loop. Such a design doesn't need to be connected directly. Current is induced inside automatically as soon as the motor starts. It's a simple, reliable, and mass-produced option for industry. But if the motor is more complex, more powerful, then classic windings are used. A worker manually lays copper wire in each slot, carefully tightening it, bending it at an angle. Here, symmetry, precise geometry of the turns, and perfect insulation are important. The wire must lie right, not touching the metal anywhere, not crossing over, not being too tight or too loose. A mistake, and the motor will overheat or fail. The rotor windings are then connected in a specific sequence: star, delta, or another type of connection. Everything is secured, insulated, and sometimes varnished. The insulated ends are led out to slip rings or brush assemblies, depending on the design. After this, the rotor is balanced, as it has to rotate at speeds of thousands of revolutions per minute. Any extra 100 grams on the edge, and everything will vibrate, hum, and heat up. The result? A compact, shiny cylinder with windings of copper wire or closed bars. It will be inserted into the stator, and the magic of converting electricity into motion will become possible. It all starts with checking dimensions and tolerances. The gap between the rotor and the stator, the so-called air gap, must be very small. If it's too narrow, friction will occur. If it's too wide, the magnetic field will be weak, and the motor will lose efficiency. The rotor is mounted inside the stator via bearing assemblies. Sometimes special guides or hydraulic presses are used for this. The rotor shaft must rotate perfectly straight, otherwise everything will vibrate or break down within a week. At the ends of the rotor shaft, sleeve or rolling bearings are installed. They allow the rotor to rotate without friction. The bearings are placed in so-called end shields, which are then attached to the motor housing. All surfaces are pre-lubricated with special greases to ensure durability. The ends of the stator and, if necessary, rotor windings are led out to the terminal box. Here they will be connected in the required circuit, star, delta, or another. In complex motors, temperature sensors are installed to detect overheating before a failure occurs. The motor is now assembled, stator and rotor in the housing, wires connected, bearings in place. But it's too early to start it. First, varnishing, drying, balancing, and testing, all like a ritual before the birth of a real machine's heart. In a spacious room with a specific smell of epoxy resin, the stator windings, and sometimes the rotor, are coated with electrical insulating varnish. This isn't just for dust protection. The varnish strengthens the structure, secures the wires so they don't vibrate at high speeds, and prevents moisture penetration. Application is either by dipping in a bath or by spraying. The motor is completely submerged in a tank of varnish, then removed and left to drain off the excess. Next is drying in a thermal chamber at a temperature of 250 to 300 degrees Fahrenheit. This stage resembles baking. The varnish polymerizes and forms a hard protective film. After varnishing, the most sensitive stage, the motor is installed on a balancing stand. The system is like a huge record player. The motor rotates at high speed, and sensors detect the slightest deviations. Even a few grams of excess mass on the rotor can cause vibration that will destroy the bearings, shorten the service life significantly, or even ruin the motor. To eliminate the imbalance, engineers drill microscopic holes in the heavier part of the rotor, removing excess metal. This is almost a jeweler's craft. The finished motor is sent to the test stand. Here it comes to life for the first time. It's connected to a power supply. Rotations, noise, heat, current consumption are recorded, and efficiency and power are measured. Everything is documented. The motor's passport contains dozens of parameters. If the motor passes all tests, it's packaged, a seal is applied, and an instruction manual is added. And very soon, this motor could be working on a conveyor, in an elevator, or in an electric train, wearing down metal and converting current into motion, without rest for tens of thousands of hours. Every year, the world produces over 200 million kilometers of cable, enough to wrap around the Earth 5,000 times. But few people know that the heart of every electric car is not just the battery, but also a cable that can withstand voltage, temperature, pressure, bends, and vibration. How are these high-tech wires created, capable of working in conditions where even metal seems alive? How do scrap, dust, and molten aluminum turn into the arteries of Tesla, Rivian, and Lucid? In this video, the whole truth about the most engineered wire of the 21st century. Every cable for an electric car is a strategic choice. It must be flexible but not brittle, conductive but not vulnerable, lightweight but capable of withstanding hundreds of amps and thousands of hours of voltage. And when engineers sit down at the drawing board, they are like alchemists of the future, mixing formulas of elements in their heads, searching for the perfect balance. Copper is the good old classic. It conducts electricity better than anything else, and it's its heart that beats in most cables. But the weight, oh, that weight! An electric car needs to be as light as a cat, so aluminum often steps in as a substitute. It's cheaper and lighter, though not as conductive. But in the right alloy, it's already a weapon of the electric age, and around it, insulation. These are highly engineered polymers that can withstand heat, cold, chemicals, vibration, dust, and even a small lightning strike under the hood. They lack the shine or weight of metals, but without them, everything would turn into a sparkling inferno. Some cables have shielding, a thin armor of copper braiding or aluminum foil. It protects signals from interference, because in an electric car, not only kilowatts are important, but every millivolt of data too. Aluminum isn't born shiny. First, it's rough ingots, each weighing over 1,000 pounds. They arrive at the factory like aliens from their ore world, extracted from bauxite, purified, remelted, and finally formed into rectangular blocks resembling metal sarcophagi. These ingots arrive in large trailers, carrying tens of thousands of pounds of the future. By appearance, they are just shiny silver blocks, neatly stacked on steel pallets. But just get closer, and you'll feel it. A warmth of energy emanates from them, encapsulated in atoms. Sometimes, instead of ingots, the factory receives aluminum coils. This is already processed aluminum wire, wound into coils 3 or 4 feet in diameter, each weighing about 500 pounds. They shine like snake coils and glisten in the light, as if they just came out of a cybernetic beehive. Separate batches are supplied as aluminum scrap, meaning leftovers from other productions, cuttings, shavings, fragments of frames. They are sorted, cleaned, remelted, because in this future, not a single crumb of metal goes to waste. As soon as aluminum enters the factory gates, it is identified, tested, and marked. In the first stage, technicians inspect the ingots or coils, checking for cracks, corrosion, impurities on the surface. It's like a quick checkup, by eye, by hand, with a scanner. If rust, oxidation spots, or transport damage are noticed, the metal is either sent for remelting or rejected. Next, chemical expertise. A piece of each ingot is taken and checked on a spectrometer. This device shoots the metal with a laser, captures the reflected waves, and shows how much aluminum, iron, silicon, copper, magnesium, and other elements it contains. The goal is to make sure it's the right grade. After passing the tests, the ingots are marked with a batch identification number, alloy grade, date and place of melting, and sometimes a QR code that leads to a full technical passport. It's like a birth certificate that will travel with the metal until the moment it becomes wire and ends up inside a Tesla, Rivian, or Lucid. When the ingots have passed inspection and received their quality mark, they are loaded into giant electric or gas furnaces. The temperature inside, over 1,220 degrees Fahrenheit, is exactly what's needed to turn aluminum into liquid silver. No alchemy. We're talking about molten metal. The damper opens, and massive cranes carefully lower the ingots into the red-hot interior. The metal slowly melts, releasing a gray vapor and a strange smell, a chemical mixture resembling heated foil and ozone. Nearby, operators in heat-resistant suits looking like astronauts carefully monitor the furnace indicators: temperature, impurity level, viscosity. No mistakes are allowed here, as the cable for an electric car must withstand thousands of miles and hundreds of charges. A slag layer appears on the surface of the molten metal: impurities, oxides, residues of alkaline metals. It is removed manually or by automatic systems to leave only a clean, homogeneous mass. Sometimes, modifiers or alloying elements are added to give the metal the desired properties: more conductivity, strength, flexibility. Molten aluminum is poured into casting molds, usually round blanks 4 to 6 inches in diameter and up to 10 feet long. These are the future rods from which cables will be drawn. The process is called casting billets. Cooling is controlled in stages to avoid cracks. All this is accompanied by hissing steam, the roar of pumps, and a rhythmic thud, the heartbeat of the cable factory. So what is drawing? It's a process where aluminum rods are pulled through a series of increasingly narrow holes. With each pass, the metal becomes thinner, longer, and stronger. Like a piece of dough being rolled out into noodles, only instead of dough, it's hot aluminum, and instead of a rolling pin, hydraulic machines weighing tens of tons. Before drawing, the blank is heated to an optimal temperature, no more than 650 degrees Fahrenheit, so it becomes plastic but doesn't melt. Then it's fed into a drawing machine, where the magical transformation begins. Each pass through the die reduces the wire's diameter by a few percent. It's like passing through increasingly tight doors, forcing the material to stretch. After a dozen such passes, a thick rod half an inch in diameter becomes a slender strand 0.1 inch thick or even less. During drawing, the wire heats up from friction, so it's constantly cooled with water or special lubricants. Without this, it would overheat, lose its shape, or even break. Lubrication also reduces wear on the tools, dies made of carbide or diamond. Some machines can draw wire at speeds over 2,000 feet per minute. It's like someone pulling a spider web from a ball of lightning. Engineers carefully monitor the tension, temperature, shape, and shine of the wire, because even the smallest crack or geometry violation is a future short circuit in a $60,000 car. When the drawing is complete, the cable thread already looks like a shining string for a future electro-magical harp. It's long, thin, conductive, but still stubborn. To be able to wrap around batteries, penetrate narrow body channels, and withstand hundreds of thousands of bends in the motion of an electric car, it needs to be annealed. The wire slowly passes through furnaces without an open flame, or through an induction field that heats it from the inside. The temperature, around 600 degrees Fahrenheit. This is the point where the metal doesn't melt, but changes its character. The atoms, which until now held onto their nodes in a stressed crystal lattice, finally relax. Like soldiers after a battle, like a string that has sounded at its maximum, and finally fallen silent. The metal structure becomes more uniform, the grains larger, and the wire itself flexible, elastic, calm. The surface of the wire after heat treatment is darkish, with scale or signs of oxidation. It is cleaned off with abrasive brushes or in chemical baths. Aluminum must shine, like a star before a rocket launch. The cleaner the surface, the better the insulation will adhere. Next, insulation. An ultra-thin layer of material is applied to the wire, separating it from everything except the current. This can be polyethylene, Teflon, silicone, or enamel, depending on the cable's intended purpose. The material is applied in liquid form, often in heated baths or through nozzles that cover the wire with a uniform flow. The application temperature, over 400 degrees Fahrenheit. As soon as it's applied, it's immediately baked. The insulation doesn't dry, it polymerizes. It's like creating a skin around the nervous system. It must be perfectly even, dense, without microcracks. Otherwise, the wire won't pass the test. Next, the wire passes through detectors that check it for breakdown, coating thickness, and electrical resistance. At least once every 1,000 feet, samples are taken manually and checked under a microscope. Everything is recorded because this wire will later work in high-voltage systems. The finished wire is cooled, lubricated to reduce friction, and then carefully wound onto drums or spools, sometimes up to 5,000 feet long. This is no longer just metal, it's the nerve of an electric car, ready to hit the road. Did you know that the machines powering global industry, transportation, and our electrical grids consume energy equivalent to building thousands of the Great Pyramids of Giza every single day? This hidden power isn't just about raw force. It's delivered by some of the most massive and awe-inspiring engines ever conceived. From the dawn of the industrial age to today's modern world, engineers have chased the dream of bigger, stronger, more efficient powerhouses. Get ready to take a journey through history and dive into the incredible scale and engineering genius behind the world's most powerful and giant engines. Our journey begins in the age of steam, a time when raw pressure was king. Picture the late 18th and 19th centuries. The engines that drove the Industrial Revolution weren't small. Early steam engines were clunky, but they quickly grew into colossal machines. Think of the beam engines, towering structures in factories and mines, with massive beams rocking back and forth, driving pumps and machinery with the power of boiling water. These were mechanical giants, their sheer physical size necessary to contain the immense forces of steam pressure. As steam technology evolved, so did the engine's power and scale. Reciprocating steam engines became the heartbeat of global shipping. Imagine the engine room of a massive early 20th century ocean liner. You'd see multi-cylinder engines with pistons the size of trash cans, connecting rods like tree trunks, and crankshafts so large they needed multiple men just to inspect them. These engines were colossal, spanning multiple decks, their rhythmic pounding driving propellers powerful enough to push thousands of tons across vast oceans. They were engineering marvels of immense moving parts, powered by the simple expansion of steam. While steam dominated for a long time, the early 20th century saw the rise of a new kind of giant, the diesel engine. Unlike external combustion steam engines, diesels burn fuel directly inside the cylinder. This was a game changer for efficiency and power density. Early large diesels quickly found their way into ships and power generation. Imagine a large, slow-speed marine diesel engine built for a cargo ship. These engines are absolutely colossal, often standing as tall as a multi-story building and stretching the length of a gymnasium. Modern marine diesel engines, like some built by Wärtsilä or MAN, are among the largest machines on Earth. The biggest ones have multiple cylinders, each with a bore, diameter. Wider than a grown man is tall. Their crankshafts are multi-piece monsters, weighing hundreds of tons. These engines produce over 100,000 horsepower, enough to move supertankers and container ships carrying 20,000 containers. The sheer scale of these components, pistons, connecting rods, crankshafts, cylinder blocks, is mind-blowing, a testament to achieving immense power and torque from internal combustion. As technology advanced further, especially in the mid-20th century, the gas turbine emerged as another powerhouse. Unlike diesels or steam engines that use pistons, gas turbines burn fuel to create hot gas that spins a turbine wheel, similar to a jet engine. While aircraft engines are built for power to weight, industrial and power generation gas turbines are built for sheer output. Imagine a power plant gas turbine the size of a bus or even a small house. Modern industrial gas turbines, like those in GE's H-Class, are engineering marvels generating hundreds of thousands of kilowatts, enough electricity for hundreds of thousands of homes from a single unit. They involve incredibly complex internal components, spinning at thousands of revolutions per minute in temperatures hotter than molten lava. Their power output, efficiency, and relative compactness compared to older technologies make them the giants of modern electrical generation. Some large ships, including cruise liners, also use gas turbines for their combination of power and smoother operation. Comparing these generations of giants is fascinating. Steam engines were the pioneers, relying on brute pressure and massive physical structures. Diesel engines brought efficiency and incredible low-end torque, dominating heavy transport. Gas turbines delivered immense power density and high-speed rotation, becoming the backbone of modern power grids and high-speed applications. Each technology pushed the boundaries of materials, science, and engineering to harness energy on an ever-increasing scale. These engines, whether the visible, rhythmic giants of the steam age or the humming complex powerhouses of today, are the unseen heart of the modern world. They drive global trade across oceans, power the trains that move goods and people, generate the electricity that lights our cities and runs our factories, and fuel the massive pumps and machinery of heavy industry. They are a testament to humanity's relentless drive to build bigger, stronger, and more powerful machines. So, the next time you see a massive cargo ship, a powerful train, or simply flip a light switch, take a moment to remember the incredible journey through history and the engineering genius behind the world's most powerful and giant engines. From towering steam engines and colossal marine diesels to blazing hot gas turbines, they are the hidden giants that built our modern world. What era or type of giant engine fascinates you the most? Let us know in the comments. Did you know that each year the world builds structures so massive, skyscrapers scraping the sky, bridges spanning vast canyons, ships larger than city blocks, that they require metal parts shaped with forces equivalent to thousands of tons and precision measured in mere millimeters? This isn't just cutting and welding metal in a workshop. This is bending steel plates thicker than your arm, forging colossal parts under unimaginable pressure, and machining giant structures with surgical accuracy. Get ready to witness the most impressive, largest-scale metal fabrication methods on Earth. uncovering the hidden power and precision that builds our modern world. The sheer scale of metal fabrication hits you right away on the factory floor. We're talking about moving and shaping pieces that weigh tons. One of the most fundamental and visually impressive processes is metal bending. Forget bending a paperclip. Imagine bending steel beams strong enough to support a building, or curving thick metal plates for ships and pressure vessels. Massive machines called press brakes or roll benders use incredible hydraulic force to shape metal. Picture a giant press pushing down with thousands of tons of pressure to put a precise bend in a steel beam, or colossal rollers curving a thick steel plate into a perfect cylinder. These aren't just big tools. They're feats of engineering designed to apply immense force with fine control. On the biggest scale, you see specialized machines like the FKB 3-roll plate bending machine, capable of shaping massive steel plates for tanks, wind turbines, or ship hulls with incredible accuracy. Software like Bentronic controls the rollers with millimeter precision, even on pieces the size of a room. Another impressive example is bending giant steel beams for structures. Machines like the Faction R CMI use powerful hydraulic rolls and guide systems to curve huge I-beams or H-beams into exact shapes needed for complex architecture or bridges. Applying that much force while maintaining the beam's structural integrity is a true industrial art form, making metal flow like clay, but under thousands of tons of pressure. Another mind-blowing method is metal forging. This is using localized compressive forces, often with immense power and heat, to shape metal. Think of a blacksmith, but on a scale where the hammer is a machine delivering thousands of tons of force. In massive forging presses, heated metal billets, solid blocks of steel, are pounded or squeezed into complex shapes. This process changes the metal's grain structure, making the finished part incredibly strong and durable. This is how critical components for aircraft landing gear, engine parts, or even massive artillery barrels are made. At places like the Waterlet Arsenal, you see iconic machines like the rotary forge. This is a different kind of forging, using rotating dies to hammer and shape a heated steel billet into a hollow tube, like a cannon barrel, with incredible speed and precision. These machines have been operating for decades, playing a vital role in producing thousands of heavy-duty barrels for military systems. The sheer force and rhythmic pounding of these colossal machines working on red-hot metal is one of the most dramatic spectacles in metal fabrication, showcasing raw power precisely controlled. Once metal parts are formed by bending or forging, they often need precision finishing. This is where machining comes in, using tools to cut away material and achieve exact dimensions and shapes. On the bigger scale, this involves massive CNC, computer numerical control, machining centers working on parts that weigh many tons. Imagine a machine tool the size of a small house, precisely cutting, drilling, or milling a giant metal casting or forging with micron-level accuracy. Sophisticated software controls these machines, making complex cuts and achieving tolerances required for critical components in aerospace, heavy machinery, or energy production. Precision machining isn't just about size, it's about achieving incredible accuracy on massive objects. Machines use advanced cutting tools made of hardened materials, sometimes cooled with high-pressure coolant, to cut through tough alloys. On critical components like gearbox housings, turbine shafts, or large crane parts, surfaces must be machined to tolerances that ensure perfect fit and smooth operation under immense loads for decades. It's a process where technology allows engineers to sculpt giants with the precision of a jeweler. Beyond these core methods, metal fabrication involves a host of other impressive processes on industrial lines. Cutting is a crucial first step, using powerful lasers, plasma torches, or water jets to slice through thick metal plates with incredible speed and clean edges. Welding is joining metal pieces together, From automated robotic welding arms building vehicle frames or ship sections, to skilled human welders performing critical structural welds that must withstand massive forces. Surface treatment like sandblasting and industrial painting or coating lines protect the metal from corrosion and give it its final look. Throughout all these stages, from the arrival of raw metal plates and beams to the final finished and assembled components, rigorous quality control is paramount. Industrial scanners, ultrasonic testing, X-rays, and precise measurement systems check every weld, every dimension, every material property. Experienced technicians and engineers oversee automated inspection systems and perform manual checks on critical points. A blend of high-tech monitoring and human expertise, ensuring that these massive metal parts meet the highest standards of strength, precision, and safety required to build skyscrapers, planes, and infrastructure. These massive metal fabrication facilities are not just factories. They are cathedrals of engineering power and precision. They process hundreds of thousands of tons of metal each year, shaping it into the backbone of our cities, transportation, and industries. It's a testament to human ingenuity and technological advancement, taking raw materials and applying immense force and incredible accuracy to build the physical world around us. It's a hidden, necessary industry that few people ever see. So, the next time you look up at a skyscraper, cross a bridge, or see a large machine at work, remember the mind-blowing industrial process that created its metal bones. The bending of giant beams, the forging of colossal parts, the precision machining of massive structures. It's all part of the amazing world of metal fabrication. It's a fascinating look into the power and precision that builds our modern world. What part of these impressive metalworking methods surprised you the most? Let us know in the comments. Did you know that each year the world faces the challenge of decommissioning millions of old electrical transformers? These metal giants, often found quietly powering our neighborhoods, can hide an incredibly dangerous secret. Many older units are filled with highly toxic chemicals, like deadly PCBs. A single misplaced cut or accidental spill could cause severe, long-lasting environmental damage across vast areas. Taking down these hazardous units isn't a typical scrapyard job. It requires a specialized, highly precise, and incredibly dangerous industrial process happening behind closed doors. Get ready to see the intense operation to safely dismantle these toxic time bombs. So, why exactly are these old transformers so dangerous? For decades, many relied on a coolant liquid called ascarel, which contains polychlorinated biphenyls, or PCBs. These chemicals are terrifyingly persistent in the environment. They don't break down easily, and they are highly toxic to humans and wildlife. Even a small leak from a neglected unit can contaminate soil and water for generations. Modern transformers use safer, non-toxic oils, but the legacy of PCBs in older units means they cannot simply be scrapped like regular metal waste. They demand specialized, heavily regulated facilities designed specifically to handle these hazardous materials with extreme care and containment. The intense process begins when old transformers, often behemoths weighing thousands or even tens of thousands of pounds, arrive at these specialized decommissioning plants. Picture massive yards filled with these silent, potentially hazardous giants, waiting to be processed on a dedicated industrial line. The absolute first step isn't dismantling or cutting. It's meticulous documentation and assessment. Each arriving unit is rigorously inspected, its history and potential contents checked to determine if it likely contains PCBs or other hazardous materials. They are categorized based on size, type, and estimated contamination level. This initial sorting on an industrial scale requires heavy-duty lifting equipment, massive cranes and powerful forklifts, just to move these incredibly heavy pieces of electrical history into position for the next stage. Once identified, Categorized and positioned, the transformers move onto the dedicated high containment processing lines. The absolute priority here is total containment and zero exposure. Every single step is designed with redundant layers of safety to prevent any spills or contact with the toxic materials inside. Workers operating on these lines are encased head to toe in specialized protective gear. Full chemical suits, filtered respirators, multi-layered gloves. The air quality within the facility is under constant real-time monitoring. These are not standard factory conditions. They are hazardous material handling zones requiring maximum vigilance. The first critical task on this line is to meticulously drain the internal coolant oil. This oil, especially if it contains PCBs, is the most dangerous component, the liquid heart of the toxic secret. Draining the hazardous oil is a highly precise, high-containment operation, executed with surgical care. Transformers are carefully positioned over multi-layered sealed collection systems, often including large secondary containment basins designed to catch any potential leaks or spills, no matter how small. Workers use specialized pumps, leak-proof fittings, and designated tools to access drain valves and carefully remove every single drop of the hazardous oil directly into secure, heavy-duty, properly labeled tanks. This cannot be rushed. It's a slow, deliberate process. Think of it like disarming a complex device. Every connection, every hose is checked and rechecked multiple times. This step is the most crucial for protecting the environment from widespread contamination and ensuring the immediate safety of the workers directly interacting with the highly toxic liquid hidden within the steel shell. After every drop of oil is confirmed, safely drained and contained, the transformer must be absolutely de-energized and rigorously verified as safe from any residual electrical voltage. Even units that have been disconnected for years can potentially hold a dangerous charge. Highly trained technicians follow strict, multi-step lockout, tagout, and grounding procedures, physically isolating the unit and discharging any potential buildup to ensure no electrical hazard remains before any physical dismantling tools come anywhere near the unit. Safety protocols here are layered and redundant, because any mistake made at this stage carries the risk of severe injury or worse. With all immediate electrical and chemical hazards neutralized, the physical dismantling begins. The process of breaking down the thick steel shell to access the valuable materials and internal components. This is heavy-duty, industrial demolition work requiring powerful tools. Workers use intense plasma cutters that slice through thick steel casings with incredible heat, powerful hydraulic shears that crunch through metal like paper, and heavy-duty saws. The internal components, massive, heavy copper windings, dense steel cores, and various insulation materials, are often incredibly weighty and must be carefully lifted out section by section using overhead cranes and specialized rigging. Imagine cutting open a giant, multi-layered steel safe filled with tangled, incredibly dense, and heavy metal structures. It's a loud, sparks-flying process, but it's executed with engineering precision to efficiently separate the different material streams. As the transformer is broken down piece by piece on the dismantling line, the various resulting materials are carefully sorted and separated onto different processing conveyors and areas. Valuable metals like the pure copper windings are isolated into their own stream and sent for high-grade recycling. Steel casings, cores, and other structural steel components are separated for scrap metal recycling. Aluminum parts are directed to their specific recycling stream. But the key challenge, the hazardous legacy, lies with the contaminated materials. Any solid components that came into direct contact with the toxic PCB oil, internal insulation paper, wooden bracing blocks, contaminated gaskets, even metal parts that absorb the chemical, are now classified as hazardous waste themselves. Handling and disposing of this hazardous solid waste requires extreme care and strict protocols. The safely drained PCB oil, the contaminated solid materials, and even the specialized protective gear worn by workers after handling these substances must be meticulously contained, documented, and transported for disposal according to stringent environmental regulations. This often involves complex logistics chains, moving the waste to highly specialized hazardous waste landfills designed to permanently isolate the toxins, or to permitted high-temperature incinerators, specifically designed and certified to safely destroy PCBs at extreme temperatures. It's a costly, complex, and highly regulated part of the process, a hidden necessary step ensuring those dangerous chemicals never re-enter the environment to cause harm. Despite the inherent dangers and complexities, dismantling old transformers represents a vital dual purpose. Primarily, it's about environmental protection and safely eliminating hazardous waste legacy units. But it's also a significant part of the circular economy and resource recovery. Valuable metals like pure copper, steel, and aluminum, weighing thousands of pounds in a single large unit, are recovered and reintroduced into the manufacturing supply chain. This reduces the need for environmentally impactful new mining operations. So, while the drive is safely neutralizing a threat, the process simultaneously recovers significant valuable resources, making it an essential, albeit dangerous, link in the critical lifecycle management of electrical infrastructure. These highly specialized decommissioning facilities are engineering marvels in their own right. They process hundreds, sometimes thousands of transformers each year, ranging from common small pole-mounted units you see everywhere to massive multi-ton substation giants. Each unit processed represents a potential environmental disaster safely averted and a source of valuable industrial materials recovered, all thanks to incredibly precise engineering processes, cutting-edge safety protocols, and the unwavering skill and courage of workers operating daily in a high-risk, high-containment environment. It's a critical industry that literally cleans up dangerous industrial history. So, the next time you see a transformer quietly working, or simply flip a light switch, take a moment to remember the unseen, dangerous, but absolutely essential industrial process happening far from view. The vital work of dismantling old, toxic giants, protecting our environment and communities from hidden chemical threats, and recovering valuable resources for the future. It's a fascinating, high-stakes look into a necessary industry few people ever see. What part of this hazardous but critical process surprised you the most? Let us know in the comments. Are you ready to peek into a world where millimeters decide life, and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year, for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, the the disc is formed into a primary casing, still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing. This involves heating it to 1000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length, a groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a 45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. Hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection. By eye, through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase: packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture. Imagine a material lighter than plastic, but 10 times stronger than steel. It's the stuff they use to make National Aeronautics and Space Administration rockets, high-performance race cars, and armor for fighter jets. But you know what the paradox is? This super material is almost impossible to recycle. Its production is mind-blowing. Scorching furnaces, molecular transformations, nanotubes, cold plasma. But what happens when these parts wear out or break? The world got hooked on carbon fiber, and now it doesn't quite know what to do with it. In this video, the whole truth about the strongest material of our time. Don't touch that dial. It's about to get even stronger. The production process for carbon fiber starts with getting the raw material, polymers, most often polyacrylonitrile. This polymer consists of long chains of molecules that undergo special processing to give them the necessary properties for later transformation into fiber. The first step is extrusion. The polymer is melted and forced through tiny holes, forming fibers about 3/millionths of an inch in diameter. These fibers are gathered into bundles, called tows, and prepared for the next stage, stabilization. Stabilization is a chemical process where the fibers are heated in the presence of oxygen at temperatures ranging from 400 degrees Fahrenheit to 600 degrees Fahrenheit. As a result, the polymer molecules change their structure, becoming more heat-resistant and ready for carbonization. The next and most crucial stage is carbonization. The fibers are heated in an oxygen-free environment to very high temperatures, from 200 to 500 degrees Fahrenheit. Under the influence of such temperatures, all the light elements like hydrogen, oxygen, and nitrogen evaporate from the fibers, leaving behind almost pure carbon. It's this process that gives the fibers their unique strength properties. After carbonization, the fibers might undergo additional treatment, such as applying a coating to improve adhesion with a composite matrix. The resulting carbon fibers are collected into fabrics or matrices of various structures. These can be unidirectional bundles, woven fabrics, rolls, and so on. The choice of structure depends on the final application and the required mechanical characteristics. Next, these fabrics are impregnated with special resins, epoxy, polyester, or others, which allows for the creation of a composite material, a carbon fiber reinforced polymer composite. This composite boasts high strength and rigidity while remaining lightweight. Lamination is the process of layering sheets of resin, impregnated carbon fiber fabric, into a mold, where under pressure and heat, the resin polymerizes and the material hardens. The result is a strong, lightweight, and durable part in the desired shape. Thanks to its unique combination of lightness and strength, carbon fiber has found wide application in many fields. In automotive manufacturing, it's used for making body panels, suspension parts, and interior elements. This significantly reduces the car's weight, improves dynamics, and lowers fuel consumption. In aviation, carbon composites are used in fuselages, wings, and other structural components of aircraft. This increases fuel efficiency and reduces carbon emissions. In the space industry, the material is used in the production of rocket bodies, satellite panels, and elements of space stations. Carbon fiber withstands the extreme conditions of space and has high durability. Bicycles, tennis rackets, skis, boats, and even sportswear are made from carbon fiber to enhance performance characteristics. And reinforcing concrete structures with carbon composites increases their strength and resistance to corrosion. This material offers high strength at low weight. After all, carbon fiber is 5 or even 10 times stronger than steel, but significantly lighter. The fiber has excellent resistance to corrosion and chemical attacks. It also boasts high stiffness and resistance to material fatigue. Plus, it allows for the formation of complex shapes and parts, and it has thermal stability and a low coefficient of thermal expansion. But the high cost of production limits the use of carbon fiber in mass manufacturing. Also, the material is brittle and can fail under strong point impacts. Undoubtedly, carbon fiber is difficult to repair and recycle, and its mass use is also hindered by the energy intensity of the carbonization process. Carbon fiber continues to evolve thanks to innovations in production technologies and new areas of application. New carbon fiber production technologies aim to increase efficiency, reduce energy consumption and material cost, and expand the raw material base. One of the most promising discoveries is the cold plasma pyrolysis method, developed by David L. Chandler at the Massachusetts Institute of Technology. This process uses ionized gas at room temperature to break down polymer fibers into carbon fibers. Such an approach significantly reduces energy consumption and harmful gas emissions compared to traditional high-temperature pyrolysis. Furthermore, research in the field of carbon nanotubes opens up new possibilities for creating fibers with improved mechanical and electrical properties. For example, a team of Chinese scientists developed double-walled carbon nanotube fibers using a dry jet wet spinning method, providing high electrical conductivity, up to 86% of copper's conductivity, tensile strength, and high toughness. These fibers demonstrate durability even after 5,000 bending cycles, making them promising for the aerospace industry and energy storage. Other innovations include the use of computer modeling and simulations to predict the properties of new materials and accelerate development. The company 3M, for example, uses ultraviolet, electron beam, and laser irradiation to create high-precision structured materials that enhance the strength and stiffness of carbon fiber-based composites. Developments are also underway for new technologies to reduce cost and improve the environmental friendliness of production, particularly using waste from the pulp industry as raw material, which reduces industrial waste and makes the process more sustainable. In the future, further improvements in production technologies are expected, along with the emergence of hybrid composites with nanomaterials and the expansion of carbon fiber applications, from transportation and construction to energy and electronics. Recycling carbon fiber is currently a complex and important process, as this material is widely used in high-tech industries, but its waste is difficult to process due to the complex structure of composites. There are several main methods for recycling and reprocessing carbon fiber reinforced composites. Mechanical recycling involves shredding the waste and separating it into resin particles and short carbon fibers. The short fibers are used as filler in construction or for manufacturing plastics. This method is simple and environmentally friendly, but it damages the fibers, reducing their strength. There's also high-temperature pyrolysis. Waste is heated to 200,000 degrees Fahrenheit in an inert atmosphere. The resin decomposes into pyrolysis products, and the fibers are recovered. The process requires precise oxygen control to avoid damaging the fibers. There is also a fluidized bed option, where the resin decomposes in a stream of hot air, and the fibers are separated by a cyclone separator. Microwave-assisted pyrolysis involves irradiating the waste with microwaves, which accelerates resin decomposition. The method is simple and effective, requiring less equipment. Chemical recycling, or solvolysis, involves dissolving the resin in special solvents, such as nitric acid with alcohol or supercritical fluids, allowing the fibers to be separated without damage. The fibers retain their length and strength, but the method is expensive and currently mostly laboratory-based. Other recycling methods for this fiber include radiation exposure to break down the matrix, ultrasonic treatment, and the development of new chemical reagents to separate the composite components. As you can see, the bigger challenges right now lie not in producing the material, but in recycling it. Recycling carbon fiber is crucial for reducing the environmental burden, as composite waste does not decompose naturally and takes up significant space in landfills. Modern technologies allow for the recovery of secondary fiber, which can be used in construction, plastics production, and even for reinforcing concrete structures.